Welcome back. Okay, so what we have here is our derivative-friendly form, our solving-friendly form of the first derivative. So what we want to do now is use that value to find any critical values. So we're going to set the first derivative of r equals 0, or set the first derivative to 0, sorry. So therefore I'm going to use my solving-friendly form, which is 4 pi r cubed minus 500 pi over top of r squared equals 0. I'm actually only interested in the top. That's the only part that's interesting in terms of going to 0. Oops, that's a 3. I'm going to factor this. This isn't going to go to 0, okay, so we can forget about that. This is the interesting part. Now the easy way to solve this is simply to cube root both sides, and you get your root. Now that's perfectly fine for this question, full marks. However, I'd like you to notice that if we were to solve this using a difference of cubes by factoring, I want you to notice that you'll get your real root here, real as in a real number, and that you're going to get two complex roots here. And because complex roots can't be graphed on a real number line, and the curve sketching is on two real number lines that are set perpendicular to each other, this is not going to have any place on that. So you omit these. But, you know, some of you going on to engineering, into physics, into math, there are two roots here. There are other answers that satisfy the equation, and in certain conditions that might be important. It's not important in this case. This is the only one that's going to matter. So going this way is fine, but the mathematician in me always thinks, do you understand that there's still more roots here, and could you find them if you needed to? And a neat way of being able to check this is to check the determinant, remember. Remember, the determinant is the part of the quadratic formula that is important in determining the types of roots, and that's this part underneath. So the determinant is actually b squared minus 4ac, and if you take a look at that, the b is 5, so it's going to be 25, the 4 is 4, a is 1, c is 25, so that's going to be minus 100. So you notice that this is actually going to be less than 0, and that's going to give you two complex roots. In grade 10 or grade 11, your teacher might have talked of no real roots, which is true. No real roots, but there are two complex roots. Okay, enough about that. Full marks for this. So we have r equals 5. We have a choice now. We have an interval here with no endpoints. So we either have to prove that it's a max or a min using the interval chart, or we prove that it's a max or a min using the second derivative test. Let's try the interval chart just for fun. So using interval chart to prove absolute minimum surface area. So what we're going to do is we're interested in the interval between r being less than 5 but greater than 0 and r being greater than 5. We're interested in the overall sign of the first derivative, and the first derivative is given to us by this equation, and I think it's probably easiest if I work with it as 4 pi. I can work with this as r cubed minus 125, and the bottom was r squared, and that's going to tell me something about the surface area's derivative function, which is going to tell me something about the surface area function. So this will be positive everywhere, positive everywhere. Taking a value like 1, that'll be negative. Taking a value like 100, Like go really big if you're given that leeway. So 100 squared or go 10 maybe. 10 times 10 is 100 times 10 is 1,000, so that's going to be positive. This will always be positive because it's squared. So negative, positive, which means that the function is decreasing on 0 to 5, and it's increasing on 5 to infinity, which means that you have a going down and then up, down and then up. You're going to have a absolute minimum at r equals 5. How do I know it's an absolute minimum? Because it's decreasing everywhere to 5, then it's increasing after 5, and it doesn't get a chance to change after that, okay? So it keeps increasing and keeps increasing after this, and it's decreasing all the way in here. I can show it like that. So if you think about it, it's decreasing all the way to here, coming this way, and then it's increasing all the way after. The other way to look at that, as you're used to seeing it from grade 10, that if I was reading it going this direction, it would be increasing that way, and nowhere would it ever, increasing this way, increasing this way, increasing this way, increasing this way, and nowhere will it be lower than this point. So an absolute min at r equals 5. And to find the surface area when r equals 5, you're just going to plug that in. And I think I'll leave that for you to do. What I would like to do is take a look at maybe using the second derivative. Since only one critical point, or one critical value on domain, we're going to use second derivative test. So the second derivative, looking up here at the first derivative, where's my derivative friendly form? Here it is. So my first derivative is going to be 4 pi. So my first derivative is going to, or my second derivative is going to be 4 pi plus 1,000 pi r to the negative 3, or 4 pi plus 1,000 pi over r cubed. What you're interested in is whether or not that will be positive or negative at r equals 5. And looking at it, you realize that this is always going to be positive with r equals 5. It's always going to be positive with r being greater than 0, right? R is greater than 0. So this whole thing will be positive. This is positive. So this whole thing is always going to be positive. So therefore, it is concave up everywhere. Therefore, r equals 5 gives an absolute minimum surface area. So, all depends which way you like. You can do either one. Both work in this case. All right, that's example 3 done. I'll come back with example 4.